So we talked about how while you're training machine learning systems, they try to minimize their error over time as you give it more and more training data. That means that it becomes very important to understand how to evaluate whether a machine learning system is any good or not. If you want your system to get better and better over time as you train it with more data or tune its algorithms, you need a good definition of what good really means. And one way we do this is through a technique called train test. The idea here is that if you have a set of data that you're training your model with, you withhold some of that training data for testing purposes. That way, you can train your model using only the training set of your data that you set aside for training purposes, which is usually most of it, but you reserve a set of that data for testing purposes. The idea is that you evaluate your model using data that your model has never seen before. This allows you to avoid a situation where your model is just specifically fitted to the data you trained it with and isn't really generally useful. So let's say you set aside 80% of your data for training your system. You would train your machine learning model, whatever it may be, using only that training data, and then you would take the test data that you withheld, the other 20%, and use that to measure the accuracy of your model in predicting labels for data it's never seen before. And that's really what you want your model to do at the end of the day. You want to evaluate your machine learning models not on how well it can predict labels on data that it already knows the answer for, the stuff that you trained it with. You want to measure its ability to predict labels on data it's never seen before. Because in the wild, that's what your model's going to be asked to do. It's going to be fed new data that it's never seen before and asked to predict something about that data based on its internal model. So it's very important to evaluate your data on a set of data that's been withheld for testing purposes that was not used for training the system. Otherwise, it's kind of like cheating on your test, right? You're basically evaluating your model based on the data that it already knows the answers for. And that's not useful. Looking at it more graphically, this is how it might be broken out. So let's say that we're training our machine learning system on, again, finding street signs and images that come from a camera on your self-driving car. We might have a complete data set of images that were collected from real self-driving cars that somebody went through and labeled with the actual street signs that are visible within those images. We could then split that data set into a training set and a test set. And usually the training set is larger than the test set. We would then feed that training set into our machine learning algorithm for training purposes, and that machine learning algorithm would then have the ability to make predictions for new data. We then take the test set, put that into our machine learning model to get predictions out of it, and measure the accuracy between the known labels that come from our training data that we had originally and the predicted labels that came out of our system. So as you're testing your model, your test set knows the answers. It knows the correct answers that were labeled in that full data set, but it will withhold those. It will just feed the feature data, the actual images themselves, into your model and see what prediction comes out of it. And then it can compare that prediction to the actual known correct value and measure the overall accuracy across everything that's in your test set. So as your accuracy improves on your test set data, you know your model is getting better and better. Now, there are a few things to talk about in practice here. First of all, we need to make sure that both your train and test sets are large enough to contain representatives of all the variations and outliers in the data that you care about. So if you don't have enough training data, that's going to be a problem because there might be outliers or weird conditions that just aren't captured by it. Or worse still, maybe some of those outliers are in your test set but not in your training set, so there's no way for your system to learn about them. So it's important to have a lot of data to work with here that really encompasses the full range of the things that you're trying to detect in the real world. You know, you don't want to train a real world system with laboratory fabricated data, for example, because you're not going to pick up on the quirks and nuances that you get in the real world. For example, you wouldn't want to train necessarily a self-driving car based on images that were just taken around a controlled test track and then throw it out onto the wild streets of New York and expect it to do the right thing, right? That wouldn't make sense. So you need to think about how representative your training data is to the situation you're trying to work within in the real world. It's also important that you select these data sets randomly. You can't just slice them in two because there could be weird biases over time, right? It could be that there's something different about the first 80% of your data versus the second 20% just due to how it was collected. So you always want to make sure you randomize these selections. You're not just taking your data and splitting it in two. You're randomly assigning random points within that data to one of two segments, train or test. And I also want to talk about the concept of overfitting here. That's kind of what we're trying to avoid with train tests. The whole idea is that we don't want our model to be overfitted to our training data. So we don't want a model that's just good at predicting what's weird about the training data set itself We want a more general purpose model that can predict things accurately for data it's never seen before. And here's sort of a graphical representation of what overfitting looks like. So let's say we have a couple of clusters of data. We have like this blue stuff here going on and this red stuff, and we're trying to create a machine learning model that can predict whether a given point should be blue or red just based on its location here. If it doesn't know what color it really is, it's trying to predict the correct color. Now the real relationship here is probably given by this black line here. If you just eyeball it, it kind of looks like the blue dots are kind of like centered around the outside edge of this curve with a little bit of random variation that sometimes puts them outside of that curve, right? And likewise, there's a little bit of randomness in the red dots as well, where more or less they stay on this side of the curve, but once in a while they'll creep over. Now, the correct prediction here would be one that has this black line, and a trained test system that doesn't necessarily know about this training data when it's evaluating it might pick that up. But if you were only evaluating your system on data that it was already trained on, it might do something crazy, right? I mean, in order to increase or maximize its accuracy, it might come up with this crazy line here that's shown in green that actually snakes its way around all of the correct answers. And even though this green line would give you 100% prediction accuracy, it wouldn't be an accurate description of what the actual pattern is you're trying to capture here, right? So it's an important point that accuracy doesn't always mean a good model. It's possible to overfit to your training data set where all you're doing is picking up the quirks and nuances in the data that you're training with and not finding the real underlying patterns in the data itself. That's what train test is trying to avoid. By only testing the system on data it's never seen before, it can try to avoid these situations where it overfits its model just to fit the data that it was trained with. Now, train test is not infallible. If you don't have enough samples, for example, it is still possible to get weird patterns here. Or there might be some weird random chance that your train and test sets look remarkably similar. So overfitting can still happen. It's not infallible. Look at this example here. We might have a training set that was randomly selected to look like that and a test set that randomly looks like that. At a very high level, there are some weird patterns here. There's a lot of randomness in the data. And some of that variation is actually shared between the training and test sets. So we can still end up with a situation where instead of this green line, which is the real pattern we're trying to find in the data, we end up with something wacky like this orange line that's kind of like meandering and going up and down all over the place, just overfitting to that test data instead. So train test is not the be-all and end-all, but there are ways to improve upon train tests so that you can avoid this sort of a thing. Remember, the fundamental problem here is that our training set and our test data set just by random chance look somewhat similar, so there's still some overfitting that can happen there. One way around that is through k-fold cross-validation. So to further protect against overfitting, we can actually split our data not just into one trained set and one test set, but we can actually split our data into k randomly assigned segments where k is some number. So for example, 5-fold cross-validation might split our data into 5 different data sets. And the idea would be that one of those segments would be held aside as our testing data set. But then we would train our data set independently on each of those other 4. So in the remaining k-1 segments, we'll train our data each time on each one of those segments and measure their performance against the test set. Then we can take the average of all of the accuracy metrics, maybe you're using r² as your accuracy metric, across all of those different training segments that you tested against, and that will give you a more broad picture of the accuracy of your system, because instead of just evaluating against one train test split, you're actually evaluating it against k train test splits. So that reduces some of the probability of actually getting these weird situations where your training data set and your test data set look similar enough to let overfitting happen. Looking at it graphically, it would look like this. So again, let's imagine that we have a set of images from self-driving cars. Maybe we split that up into k different folds, we call them. So we have one fold that's set aside as our testing data set, but the remaining folds are all trained independently. So we might split that up into fold 1, fold 2, all the way to fold k-1, whatever that might be. And we'll actually train our machine learning model using each fold independently, and then measure the accuracy against our test set that we set aside independently on each one of those folds. We can then take the average of the accuracy metrics from all of those folds and use that as the final measure of the accuracy of our model as a whole. So this is a way to further inoculate your machine learning system from overfitting during the process of training. Obviously, this can take more time because you need to train your model multiple times instead of once while evaluating it. And you also need, obviously, more data to work with, or a lot of data, because you're going to be splitting that data up into more different folds, and you want to make sure that each fold is still enough data to train your model with effectively. So Very important to have a lot of data to work with while you're doing k-fold cross-validation, but if you do, it can be a very useful tool for evaluating your machine learning system in a way that avoids what we call overfitting.